Alrighty, so welcome to the first colloquium of the fall 2022 semester. So our first speaker is Dr. Fred Ringwald. So I should say these colloquia they're going to be short 5-10 minute talks, and essentially they're a chance for faculty to tell you about the research program and to try to recruit you to, or if you find it interesting, you can go talk to them to see about researching it further. So our first speaker is the inimitable Dr. Fred Ringwald, and he's going to tell you about the outstanding astronomy program that he's head of. Fred, take it away.
Fresno State Physics has a vigorous program in astronomy and astrophysics with our campus observatory, and these are not my students. Fresno State Station at Sierra Remote Observatories, various NASA spacecraft, the new generation of automated observatories and other observatories worldwide. Students are welcome to participate in hands-on research on exoplanets, which are planets of other stars, now over 5,000 of which are known, cataclysmic variables, flare stars, starburst galaxies, quasars, and of course black holes. The current research students are working on several topics. Armando Guerrero is writing what is looking like a very nice master's thesis for the end of the semester on the question of our superflares, the superflares of sun-like stars caused by magnetized planets. These are stars that are apparently very much like the sun, and they have flares that are at least 1,000 times more energetic than solar flares. Armando has been using observations from NASA's TESS spacecraft and now the European Space Agency's Gaia spacecraft to tell more about these. The question is of our superflares of sun-like stars caused by magnetized planets. The answer is turning out to be no, but why these sun-like stars have such un-sun-like behavior is turning out to be an even more interesting story that I will let Armando tell you later this semester when he delivers his master's thesis defense. Physics undergraduate Ben Rodriguez is looking at observations of similar stars, search for star-planet magnetic interaction. Jupiter is well known to have a powerful magnetic field if you were to move it closer to the sun than Mercury. One might expect the magnetic field of the sun and the magnetic field of a hot Jupiter planet to interact with each other. Hot Jupiter planets were one of the big surprise findings of recent decades in astrophysics. And therefore, if the superflare stars are not caused by magnetized planets, might we be able to find other star-planet magnetic interaction? I've taken some observations with Fresno State Station at Sierra Remote Observatories, and Ben Rodriguez will be analyzing them this semester and maybe starting up new observations. Saurav Karat has been working on the flickering in the accretion disk of cataclysmic variables. All cataclysmic variables have a relatively normal star, not terribly unlike the sun, filling its gravitational equipotential and spilling onto a burned out cinder of a star, in this case a white dwarf, burned out cinder of what once was a low mass star like the sun. And it forms an accretion disk. All planets and all stars form an accretion disks, and that we don't understand the physics of them very well is a scientific embarrassment, because essentially all stars and all planets form one. And these are the ones to study if you want to learn the physics of accretion disks. And one interesting bit of physics that they and all accreting systems show, all systems accumulating under gravity show, is erratic flickering. If you take repeated measurements of how bright they are as a function of time, they literally flicker like candle flames. roughly same amplitude, on the order of about 1 to 10%, roughly same time scale, a few seconds to minutes. This is most of the power output in such a system. This is not a minor effect, and that we do not understand it at all is a scientific embarrassment, a problem screaming to be answered. And there are new analysis methods, namely observations and statistics with fractal geometry, with nonlinear physics, and in particular fractal geometry to measure the roughness of these plots, these light curves. And we're hoping to tease a little physics out of them. Don't tease it too much though, or it'll bite you. I also intend to offer these 100-level courses in 2023. Right now, we have a vigorous Physics 151 observational astronomy class running in our humble little campus observatory, the poster of which is in back. All these pictures on the left were taken with our humble little campus observatory in the middle of town, under the bright lights of town, largely by students. I show this to university administrators and they stammer, "You say students did this?" I said, "Yes, my students did that." And then they make the funding. And that's important to keep the place running. And you want to schedule the observational astronomy course during the good weather time of year. We typically get essentially perfect weather for astronomy from mid-March well into mid-November. But you want to schedule a theory course for the bad weather time of year. So Physics 150 is the theory course, theoretical astrophysics, that will offer spring semester, how things in space actually work. And in 2023 fall, I plan to once again give what is, up until now, has been a special topics course. Maybe I should apply to get it formally in the catalog. My introductory course on space flight. Phys 175T, orbital mechanics and spaceflight. 3 students now have gotten jobs as a direct result of having taken this class. Physics undergraduate Christopher Parry got a job doing astrodynamics at Boeing. Eric Eichen, master's students, Eric Eichen got a job with AT&T Telecommunications, with communication satellites. And now master's student Elisa Lee got a program looking down at Earth. It's called remote sensing, where you use a spacecraft to look down at Earth. And her work on time series analysis of distant galaxies got the recruiter's attention, because now she will be doing time series analysis of ocean waves on Earth. And yes, Earth very much counts as a planet, and it is a planet probably in need of a little tender loving care. Let's stop there for now.
Fred, actually, you kept the time very well. So actually, let's do a few questions, and then if the questions run a little bit long, then we'll defer them to the end. But so, any questions for Fred? So I have a question. There
Do
you
you
go.
think an undergrad to, or like, is it okay to be an undergrad to be at these?
It is very much okay to be an undergrad, and even without experience. I have had undergrads with very little experience do things that are still, do research that is still useful to me, such as library research. We published an article some time ago measuring the research productivity of telescopes, of various observatory class telescopes, I just had them look at a bunch of journal papers and read them well enough so that you can tell whether or not any new data are presented, and if so, what telescope was used at what observatory. They all say so. And then count up numbers of papers and numbers of citations. And yeah, I got a nice paper on the research productivity of research of both small telescopes and space telescopes. And yes, about half of the papers currently being published in refereed journals, astronomy and astrophysics journals, are coming from space telescopes in space, like Hubble and James Webb. But small telescopes like ours still are valuable, especially when you take into account how much these things cost. Take the cost of the campus observatory, $50,000, and square it. That's $2.5 billion. That was the upfront cost for Hubble Space Telescope. And there were 5 space shuttle servicing missions, each costing about $1 billion apiece. So total cost of about 7 or 8 billion. And one of the great things about astronomy is you can still make good contributions with just a handful of people. Maybe one professor, maybe one postdoc. One professor like Ernest Rutherford, one postdoc like Hans Geiger, and one undergraduate like Brian Marsden. And they worked out the structure of the atom. So you can still do that in astronomy. Question?
For physics 150, can we be taking 4C concurrently?
I'd rather you didn't, because a lot of the physics in physics 150 depends on 4C and already knowing that. For example, stars radiate approximately as black bodies, so you got to understand thermal radiation and how Box Planck worked that out. Hot stars ionize the gas around them and light up the gas around them, these big clouds of gas in space. Therefore, you've got to know about the photoelectric effect, what Einstein got his Nobel Prize for. Many of the digital detectors we use at telescopes use the photoelectric effect to detect photons. You need nuclear physics because that's how stars shine. It goes on and on and on and on. So I'd rather you didn't take physics 4C. Take it. I plan to offer Phys 150 every spring. So we finish Phys 4C. Take physics 150 the next time it comes around next spring. Any other questions?
Well, let's stop it there. If Fred's still around at the end, then we can ask more questions generally. But let's thank Fred again. We got it. So our next speaker is Dr. Yongsheng Gao, and he's going to tell you about the vigorous ATLAS program, and actually also Fermilab now. So Yongsheng, take it away.
Okay. So I'll give a short introduction to our experimental particle physics program, which sends students to work at CERN in Geneva, Switzerland, and more recently, Fermilab near Chicago. CERN stands for European Organization for Nuclear Research in French, and is the world center of particle physics, and also the birthplace of several Nobel Prizes. The most important invention was probably the World Wide Web. So the $10 billion, 70 miles long Large Hadron Collider is about 300 feet underground by the border of Switzerland and France. And protons are accelerated to speed of light, 99.9999% of speed of light, in both directions, and smash head-on to create small big bangs, which bring us to the very beginning of the universe and allow us to study the fundamental building blocks of the universe. So if we zoom into this interactive region where this small big bang happens, you'll see the ATLAS detector. So ATLAS detector is the largest particle detector ever built, and it's the size of a 6-story building. And that's the size of a normal person. So the design is designed to measure the hundreds of particles flying out created every small big bang precisely, so we can recreate the crime scene. So the big investment paid off. So almost exactly 10 years ago, ATLAS and CMS experiment announced the discovery of the Higgs boson, which is responsible for the origin of mass. And this discovery was published in Physics Letters back to back, and it was named by Science magazine as the 2012 breakthrough of the year. And this resulted in the award of Physics Nobel Prize of 2013 to those two gentlemen who came up with the Higgs theory almost 50 years ago. So Fresno State joined ATLAS experiment back in 2007 as the only CSU campus on ATLAS or CMS. So the Higgs discovery was also the first research a CSU campus was involved in, which has resulted in the Nobel Prize. The other collaboration consists of about 3,000 physicists from about 200 institutions from 38 countries all over the world. And among them, about 500 from US universities and national labs. So they include 4 national labs, ARDA, Brookhaven, National Lawrence Berkeley, and Stanford Linear Accelerator Center. They also include many of the top research universities in the US. So Fresno joined in 2007 as the only CSU campus on ATLAS or CMS. So in order to provide this outstanding opportunity to a wider CSU community, Fresno State Physics Department has been building up and leading the CSU Nuclear and Particle Physics Consortium in UPAC since 2008. And UPAC now has grown to 20 CSU campuses. And we have been sending students from CSU UPAC campuses to work at CERN every summer since 2008, except in 2020 due to COVID. So last summer, 9 students from 6 campuses worked remotely with our mentors at CERN. And this year, 11 students from 8 campuses work in person at CERN for the first time since COVID. So far, over 100 students from 14 CSU campuses have worked with our program at CERN during the summer. So this table shows the recent years, the number of students and their campuses working at CERN. And 6 students per year received an NSF International Research Experience for students, which is $5,500 per student. And a few days ago, I received the Fresno State IRA Instructionally Related Activities Award to support up to 6 Fresno State students to work at CERN next summer. So while our Fresno State physics student needs to compete with students from other CSU campuses for the NSF award, this award, $1,500 per student up to 6 students, is only for Fresno State physics students. And currently we don't have 6 students to work at CERN next summer, so we encourage more students to take advantage of this IRA award. So this table shows the 12 students, their campuses, and the mentors they work with. They work with mentors from Lawrence Berkeley, UC1, Stanford, University of Chicago, and other places. So among them, there are 6 Fresno State students. The students' names shown in red were supported by an NSF RES grant, including Olivia from Fresno State. So those are the 12 students who worked at CERN in the summer of 2016. And the 5 students standing on your right-hand side all came from Fresno State, plus Olivia sitting in front. Olivia was many of the students moved on to PhD programs. So the students moved on to high-tech companies teaching, and many of them to PhD programs, including many of the UC campuses and also universities all over the country, including institutions in Austria, France, and Germany. Also, during our stay at CERN, we also visited other European cities before we returned to the US. So more recently, we sent students to work on e-course, which is the neutrino experiment and Fermilab. So last summer, 2 undergraduate students worked on the neutrino experiment, and while in Gaby, they received support from the Department of Energy, which is $6,000 per student. And they did an outstanding job analyzing the first data coming from the cosmic ray trigger. So each of them gave 3 talks in the e-course working group meeting. And because of their outstanding job, they graduated in May, but they were invited back to work at Fermilab this summer with DOE support. So we plan to send more undergraduate students to work at Fermilab next summer with support from the Department of Energy. So if you are interested in working at CERN or Fermilab next summer, so please take the online class I'm teaching this fall, which is open to all the 20 UPAC campuses. And also join our experimental particle physics group, and then submit your application by December 15th of 2020. too, and then shoot me an email. That's all I have.
So
I can still sign up for 163?
Yes, I believe so.
yeah, I think there's till September 19th, I think. Is it Vegas? Vegas is not in your head. So I'll take your word for it. It's September 19th.
Because yeah, the class is online, so we have videos posted and lectures posted, so you can review them anytime.
Yes. Matt?
Yes, is it still true that to get CERN or Fermilab sponsorship, you have to be a US citizen?
Yeah, for Fermilab, DOE only support US citizen or permanent resident. So for CERN, unless if you would like to get an SF, IRES award, you need to be US citizen. But you can work at CERN with the IRA or support from other places. So you don't need to be US citizen unless you would like to get an SF, IRES grant.
I see, thank you.
So for instance, the 1500 from IRA, there's no restriction. So any student can use it.
I don't know how long $1,500 would last in Europe.
Okay, so any other questions? So actually, you actually had a quick question. So to be eligible, they only have to take 163 or also 164?
Lessons for if they're selected to work at CERN next summer, they'll need to take 160.
Oh, they will, okay. All right.
So, but for Fermilab, that's only for the for working at CERN. For Fermilab, there's no restriction. They don't need to take 163.
Okay,
It's a plus, but you don't have to.
okay. And then Fermilab is neutrino stuff.
That's right.
Okay. All right, any other questions? All right, well, let's take now again. Our next speaker is Dr. Mihai Grassi, and he's going to tell us. Sorry, Mihai. Okay, and he's going to tell us about the vigorous medical physics program that Fresno State has that's run by Dr. Grassi. So,
Hi everybody, my name is Mihai Grassi. I coordinate around the biomedical physics program which started early 2000 by Dr. Amir Huda. Medical physics, unlike particle physics, more applied physics to medicine. So you can come to it from many angles, computer science, you can do modeling, you can do a lot of experimental physics. Traditionally, there are two branches of medical physics. One is medical imaging, looking at human body with ultrasound, X-ray, MRI, nuclear medicine, X-ray imaging of different sorts. And then radiation therapy, which is a big, important branch of medical physics, which started in the 1950s, so last century. And about 60–70% of medical physicists in the clinics work in radiation therapy. Now, what I'm doing is a bit different. I use X-rays to look at the human body, but in a slightly different way. I actually look at the composition of the human body using X-ray fluorescence. And I have here a diagram. It's based on photoelectric effect that Dr. Ivo just mentioned, that Einstein explained in 1905. So you kick a photon that absorbing is able to kick an electron out. The electron leaves a vacancy. And there are two ways to basically, the atom being in exciting state, there are two ways to come back to a ground state. One way is to emit a photon, and that has a specific energy, and we call that X-ray fluorescence or characteristic X-ray emission. And the other one is by kicking an Auger electron. You can actually use both Auger electron and these characteristic photons to figure out which type of atom you have, because each atom has different energies. So basically, the energy of the photon or the energy of the Auger electron can basically it's like a print of the particular atom. Now, the nice part about photoelectric effect is that in certain energies, its probability, so in other words, its occurrence is actually much higher than all the other X-ray effects. For example, scattering, coherent scattering, and quantum scattering. You see here the blue curve, and look at it, this is actually a powers of 10, so it's logarithmic scale. is much higher in that is for lead. So it's a big atom, but for other atoms a bit smaller, but still very high probability. So you actually, because of this, you are able to detect very, very small concentration. So that characteristic photon, if you detect that characteristic photon, you can figure out concentrations. What I built in 2014 when I came here, it's microbeam X-ray fluorescent research. It's based on you can see here, it's basically a view from the front. So this one here is the polycapillary X-ray lens. In the back here you have the X-ray tube, and basically coming towards you, it's a very small X-ray beam, around 4 millimeter distance from the end of the polycapillary X-ray. We have about 20 microns. So it's a small X-ray beam, which basically means it gives you less scatter, and you can actually even do microscopy study, which I actually haven't done so far. Here we have a positioning stage that moves in 1 micron, can move on X and Y. I have even a Z component that I haven't used, and that's the detector, you detect the X-rays. And we also have other capabilities, mostly dosimetry that we used. It's a OCL, optically luminescent simulated dosimetry. And then we also have an ion chamber. That's something that medical physicists use a lot to measure the X-ray beam, based on ionizing properties of X-rays. So this is what I use for the research. I also sometimes, from time to time, I go to a synchrotron. The one I used the most was the Canadian light source. At the end of the month, I'll give a talk of what you can do a synchrotron. You can do really neat stuff. You can do chemistry, physics. You can not only do microscopic studies of where the elements are, but you can even figure out what they're binding to. So very neat stuff. But for now, most of my talk and most of the research I do now is using the microbeam. Now I'll just give you a bit of flavor what we do. Like the recent project I did with Veda Mahajan is measuring, trying to figure out if we can measure iron and zinc, which are essential elements in the body. We really need them. Iron is, as you know, part of the blood. It's responsible for transport of gases, oxygen, and carbon dioxide. It has other roles. Zinc is also involved in a lot of immune response. You probably heard this COVID, zinc levels and so on. And there are different ways to measure them in the human body, but one basic way fundamental remains to measure their concentration in the human blood. And the idea is, can we measure with an XRF modality, can we measure them directly in the superficial blood, the one that's right under your skin? When you cut yourself, you bleed a bit. So there is blood right under, like within a millimeter or so. Now, there are other modalities to measure these very small concentrations. And for example, you have this ICP-MS measurement. They can measure nanograms per gram. However, they're fairly expensive and they're also invasive. You actually have to draw blood. So, like, we're looking at maybe if we develop a method that we don't need to measure blood. So basically, if you have, this is kind of like an anatomy of the skin, and you have these two plexus, basically the blood vessels are organized in a more deeper plexus and then a plexus and then a more superficial one, and you have this kind of vertical small arterioles where blood flows to the surface of the skin. And we're trying to basically do experiments to figure out if we can actually detect this, if we're actually within the physiological levels of these two elements. And we did different experiments. First one, we basically put this iron and zinc, and we actually looked at other elements, copper and selenium at the beginning. Then we excluded those because we realized it cannot go to such low concentrations. But we did this pipette tip, and then we realized, well, this one, the attenuation of the plastic was too small by comparison with skin. So and then we moved to this foam plastic called polyoxymethylene, which is actually very similar to skin. We measured that last year or 2 years ago, and it's actually very, very close to skin at these X-ray images. So we moved in these steps. We did first a 0.9 millimeter thickness, and we realized, well, sometimes the blood can be actually more superficial, so we do a 0.5 millimeter, and we also can insert something, so basically the volume of the liquid can be smaller, just like in a human, like in a human skin. And the results we got are pretty encouraging. You see here what we get for micropipette, for this cylinder, for a cylinder with a 0.5 millimeter wall, but without an insert. We still have to do the insert part of it. And you see the detection limits, roughly around 20 or so, 80 for the thicker one, milligrams per liter. And the physiological levels run somewhere between 300 and 600 milligrams per liter for iron. And for zinc, it's similar. And zinc is a bit harder, as you see. We're getting we're approaching a bit closer to the physiological levels. When we insert, we might maybe get a bit higher. So zinc is right now not clear, but definitely iron is doable, and it's something that could be useful. The radiation dose when you do this such a test. So right now I think we're running 3 minute test, 3 repeats of 3 minutes. So something that would be very fast, cheaper, and something that will give you and something that anybody could use, a family doctor, not because ICP-MS and other methods, they need experts in labs, technicians. So that's just the flavor of my research. If you need to reach me or if you're interested in any project, I go for 1 summer to like a year or 2, and just contact me in the shop.
Any questions?
Is there parts of it that are hardware where some of these guys got to make some of that stuff at all, or?
Yeah, mostly in the sample so far. And I had Dave and now Matt who do, most of the finer stuff. They can, definitely be, and also designing this. It's a lot, in my lab, it's a lot of data analysis. I mean, we run the experiments too, but then we have to analyze the data, compare and do all this. But yeah, they can be involved in that part too. If they want to make something more fancy, for example, now here we could actually, I looked it up and there are some, you can buy these very, very tiny, they're made of glass capillaries that almost imitate the human capillaries, and you could buy this, and if you feel them, that would be a very realistic, phantom. So phantoms are very, very, making phantoms very tricky now. They can actually make phantoms that look like the real tissue. It's unbelievable in X-ray imaging. So, yeah, you can do different things. I also work on modeling. I didn't talk about that, but if people are more computer inclined or theoretical, we can use that work.
Any other questions?
So your work has only been in phantoms. You haven't actually used skin samples or volunteers?
No, I've used real samples. In fact, I have a project right now with the land bone sample, and that's Michelle's project. We're supposed to graduate, I think, in the spring. I've used in the past nail sample, human nail samples. So I did use real samples, but before you use real samples, it's good to have an idea if you can actually do what you can claim to do. So phantom is the first step. Then it's usually either type of tissue sample or animal work if you want to go more towards in vivo applications.
Have you heard of the project using breast milk to test for breast cancer?
Sorry?
Using breast milk to test for breast cancer.
Milk. No, I don't know what you're looking at exactly. Yeah, it's probably more chemistry. You're looking at a certain compound.
Yeah.
Yeah, there are different. There is a lot of cancer research involved. These, nutrients, microelements, and I'll probably touch on that when I talk about the synchrotron work, because you do have to have this microscopic capability, which my system can do, not at the level of the synchrotron, but I can do. That's something I'm actually interested in. We can do some microscopy based on scattering of X-rays.
Other questions? So also, let me mention, Dr. Grassi is going to give a full-length talk September 30th on some of his research. So
Right here?
yeah, right here. They're all here. They're all here. All right, let's thank Dr. Grassi again. next
the ones
speaker is
that
Dr.
come
Paige Ho, and she runs Fresno State Strongly Correlated Electron Lab. And Paige Hun, take it away. That's right.
Okay. My name is Paige Ho. So these are my research website. Recently it got removed. I think Roger helped me put it back to the new reward website. They're changing every year almost. So, but otherwise has a more detail what I do there. So the important thing is my research is more in the material science, more academic study. I don't do any device design of the material, but application of the material. But I do study the physical property of the material, and more focusing on the rare earth related material. So why are we interested in material science? I think there's a famous Japanese scholar talking about if we control the material, basically we control the technology. So, and then the important thing about our society now is the energy. So one aspect I study is more related to the superconductivity. So imagine if we have a room temperature superconductor we can apply, then we will be able to have the power transmitted from the power plant to your home without loss of energy. Okay. But currently, like this superconducting material, we can build is a very strong magnet. So they apply in the magnetic resonance imaging, and then for this magnetic levitated trend can reduce in the friction. Okay, can even have a higher speed rail. Okay, even though Fresno even don't have the high-speed rail yet.
It's coming.
How is coming?
It's coming.
Hopefully.
Right.
And then the magnetic material, we could using this magnetic material in like a data storage or in some magnetic refrigeration without the mechanical vibration kind. And possible application in this, also the MRI imaging by applying the magnetic moment inside so you will see better contrast. And also now the electric car is famous, so you have a permanent magnet motor. Okay. So now I will move on the research I'm focusing in my lab. Currently, I'm more focusing on the phosphatidylate compound. It basically is composed of a rare earth material with a transition metal and with a nitrogen family. So you look at here, will be rare earths all here. Okay, not to the uranium part, no, not to the actinide, only the rare earths. Okay, and then you have the osmium. Let's see, osmium. Where is it? Oh, here. Transition metal. So it's kind of an alloy compound, kind of complicated material. So there's a lot of interesting behavior. So the electron interaction is really strong in this kind of material. So some of the people already taking my physics 102, the modern physics. I was starting with a simple metal model, the Fermi liquid model there. But on the other hand, in the real world, the electron interaction, when you start involving with a transition metal, D and F electron, the interaction will start to become very strong. And the simple metal model won't apply. So there's a lot of interesting behavior there, so we want to study it. So for example, the unconventional superconductivity, I studied in the praseodymium, osmium, and timnite compound. And now I'm doing some substitution study. And then recently, the topological insulator, they particularly hoping this will be the next generation semiconducting material. But still currently is more academic study. And then the Sierra osmium timnite material has kind of interesting topological insulating behavior. And then recently, if we say we doping with a praseodymium, we want to see whether we will influence in the unconventional superconductivity. So there's some side project like a rare earth nanoparticle or some dye-sensitized solar cell. Really, due to pandemic, my lab almost got shut down, losing a lot of students. I started rethinking, oh, what am I going to sustain my lab as an experimentalist? So currently, I'm more focusing on the field scattering material. Yeah. To be an experimentalist, sometimes you need to facing a lot of realistic stuff. Like, for example, the cost. Do not even thinking always you want the fancy stuff. Sometimes even kitchenware. Indeed, I'm using a lot of kitchenware in my lab. It can save a lot of money, you know. You just need to improvise.
It doesn't matter if it's fancy or not, as long as it works.
Yeah, that's the most important thing.
Yeah.
But sometimes students doesn't understand, but they start working in the lab, they get it.
But do when they start paying the bills.
Huh?
When they start paying the bills, I understand.
Oh, yeah. So that's a more important thing. So that's why also our lab is more small budget. So whatever the measurement instrumentation is built by the undergraduate student. Okay. And now recently even have more university high school students involving with my research. So the very important thing, the physics behind the rare earth material involving something we call the quantum critical behavior. So a lot of times they found there's a certain order phase, like a magnetic order, or even can be some electric order, electric quadruple order. But if you say you're suppressing that order phase to a 0 Kelvin, it will have involving with some quantum fluctuation. End up, you will be able to start to bring out the unconventional Fermi liquid behavior. What they call it non-Fermi liquid behavior. Now the fancy name even call it strange metal. Okay. Every few years, for the founding agent, they want the flashing name from non-Fermi liquid, they will change it to strange metal. Also, when you have this strange metal behavior appear, you possibly will start having this unconventional superconductivity to appear. Okay. So in order to tune to this quantum critical point, the 0 Kelvin phase transition, so a lot of time we were either by the magnetic field, tuning by the magnetic field, or tuning by the substitution. That's more the focus in my lab, magnetic field and the chemical substitution, or even by the pressure. I don't have a pressure technique, but usually I also collaborating with the people having the pressure technique so we can study the property of the material. Okay. So more recently, these are the papers just recently got accepted for the PRB. And we found first we were neodymium osmium antimony is a magnetic material. So, and then neodymium always famous for its magnetic property. So we thought we doping the neodymium into praseodymium osmium antimony, we could enhance this unconventional superconductivity. End up a very strange thing it happened is end up if we put a neodymium substitution, we completely suppress that broken time reversal symmetry. Okay, end up it become normal, it become conventional superconductivity more. So this is something unexpected in this material. So because the paper haven't published, so I haven't put a paper here. But this is an interesting thing in order to study that broken time reversal symmetry. End up, even I'm a condensed matter physics, I'm not good with particle. We still need to go to the particle physics facility to study, to using the MIMOM to study the magnetic structure of the material. So it's really highly interdisciplinary for the condensed matter physics. Whenever we need something, we just need to learn it, to develop it, to learn a new technique. Okay. Okay. So also recently, I say the Sierra osmium antimony, we built, in order to study the physical property, we built a lot of phase diagram. So we found this is a very bizarre phase. It has this metal insulator transition, and now we have this very strange like a reverse wedge still. Typically, it's just like a dome, okay, like a half elliptical shape. But end up is very odd. This is something even. So currently, the material I study is more experimental dominated, and haven't found a good theorist to be able to explain it. So these are all the related paper related to this material. Okay. So currently we start doping the praseodymium into it, and this summer, Letty and I, we just went to the high magnetic field lab to study some property. Okay. Hopefully, she come back from the Japan, we will be able to go to March meeting to presenting it. So now let's start talking about the laboratory part, because we are experimentalists. Every student, including me, together we need to maintain all the experimental equipment. Okay, so equipment will not stay new. So there's on the other hand, by repairing or set up the equipment, you can learn a lot of techniques behind a lot of physics behind the lab. Okay, so that's the part students have to learn. And then not only that, these are all the student built instrumentation. So we build a magnetic susceptometer, so measure the susceptibility, and then electrical resistivity probe, and then heat capacity, so build the calorimeter and the thermal power, already changing every several design up till this moment. I think this is probably the 6th design. Okay. So used to be I have this 1.6 Kelvin refrigerator. Now because the helium is not renewable source, is too expensive to be afford. So I'm more focusing on using the cloud cooler. If luckily next cycle I got a new grant, I'm going to buy another closed cycle, maybe with the electromagnet. So a lot of times that we will just need to really thinking ahead what we plan to do in the future to sustain the lab. So another important thing for the lab, the student in the lab need to do will be automatic measurement. So make the LabVIEW program to automatically taking the measurement. But a lot of times the student doesn't understand. They're really thinking they let the automatic measurement run. They don't need to monitor it. They monitor the data. No, you need to monitor the data and you need to analyzing along. So if you have a bad data, you immediately need to remeasure the data point before we warm up the system. Okay. So if we have a good results, basically I will take the student to the conference. So over a year, almost every March meeting, if we physically attend, I let the student go. If we couldn't attend, they attend virtually. Okay. So this is during the pandemic, I'm losing a lot of undergraduate students, end up a university high school student attending my lab. So he was able to using the research results and attend. Now he got accepted to the undergraduate program for University of Maryland. Okay, so you guys in California do not thinking everything about UC. East Coast also have a lot of good school. Okay, anyway, or even Middle West. So besides doing the research like once or twice a semester, we still doing the physics outreach. So try to train the student using the layman language to talk to the kids. Okay, so make the student more interested in physics. Okay, so currently the undergraduate student is Zach Carender and Letty. Letty currently this semester went to Japan to do study abroad program, but she will be back next semester. And then we had a new member joining is Sudesh. Okay, and then recently getting more and more university high school students want to join my lab. Okay, so I still need more undergraduate students to join my lab. It's really need a lot of manpower and really hands-on. So it's not only the physics, it's also you need to learn how to operate in the lab. It's a lot of skill. I always joking about you need to starting with a janitor, keep the lab clean, up to the director level, everything, full spectrum. You need to write a proposal, you need to write a report, you need to do the experiment, so everything, 24/7, okay? Once you committed to research, it's 24/7. Okay, that's the end of my talk.
Thanks, Petra. And are there any questions?
Oh, yes.
Yeah.
Yeah.
How do you get credit for mentoring a high school student?
It's hard. Lots of paperwork.
Until they only can sign up for independent study till the junior level. So like last year, basically I don't get credit for it. And this year they be able to sign up for independent study. But only the university high school student you can do that. If it's a North, like Clovis North, it won't work because they cannot sign up for independent
But
study.
you're basically doing this out of the goodness of your heart.
Yeah. Also the commitment to my grant too. Okay, I need to outreach to public.
Sorry, what did you say?
The grant, the NSF grant, it need a commitment to the community. So both. For the goodness of my heart, and also for the
thing is,
grant.
I have no goodness in my heart, so I can't.
Without the money, we basically couldn't get the experiment going, you know. So
Yeah, okay.
yeah. Yes.
So you said there's a bunch of undergraduate students taking your lab. Is there any prerequisites you recommend taking, or?
I even recruited students when they were in the 4A level. I trained them just a hands-on, yeah. Oh, Joseph has the first experience. Oh. He joined my lab one summer. But I was too skimpy and ended up he run away to a tourist group. I got really upset.
It's all after his fault.
Yeah. I should have that chance, I should pay him and he will stay. But usually I try out the student because sometimes students don't know. But Joseph is really good, so yeah.
Yeah, I just wanted to make a comment about high school students. I think that's a great thing. I've actually had a couple of Clovis North students come to my class, even though we're not getting credit or anything. I think it's a good thing to bring them in because generally they're really ambitious, aren't they? And they want to work hard and everything. So I think it's a very, very good thing.
Oh. Okay. Anything more?
Can you put your email again, please?
Oh, email. Oh, our email on website. The faculty email is no PC like a computer PC HO. My last name like a Christmas ho ho ho, but only one. So and at csufresno.edu. Yeah, but otherwise you go to the physics website. You can find all faculty's email there. Okay.
And so Patron's office is just down here, up, and then like almost like there. So it's like 254.
254. No, office is 255. Lab is 254. Yeah, yeah. If you come over, I give you lab tour.
Hey, and all of us are on the physics website, right?
Oh.
Everybody's on there. You can always find us on there.
But most of you know me. You know I'm almost every day. I'm in my lab. Okay. So you almost can find me almost every day. Yeah. Okay.
All right, thanks, Patron. Okay, almost last but not least, so Don, I see you came, so like Don's gonna.
Oh, we're gonna go next?
No,
Don, yeah.
So down, man. No, so, yeah, so anyway, so we have, I'm gonna talk about the research program in theoretical physics. And apologies to Tori, this actually I should include you in this now, but you know, and also I should update my slides. But basically, let me say, the pencil and paper theorists are myself and Gerardo Munoz. Gerardo, raise your hand. Okay. And so here's our email address if you want to contact us. And the selling point. So let me just say, unlike Dr. Grassi, Dr. Gao, Dr. Ho, we can't pay you anything. We don't have any grant money. But we do very, very cool stuff. And if you're thinking of going to a PhD program, we have a super strong record of student publications and also conference attendance. Not only conference attendance, but giving talks and also getting awards for those talks. So yeah, the money thing is a little bit of a deficit in our research program. But pure goodness. Pure goodness, right? Anyway, So basically, so if you go through the theoretical physics program, like it's a good background for going into a PhD program, for community college teaching, and also going into industry, surprisingly. All right, so the research areas that we cover are basically classical and quantum field theory, gravitational physics, and cosmology. And actually, I even have, a long time ago, I even had a publication in condensed matter physics in Phys Rev B. So, all right, so actually, since this is sort of an advertisement, I'm just going to talk about the students, talk a little bit about the research that was involved, and what happened to those students, because I mean, that's at the end of the day what you guys are interested in, is like, what can they do for me, right? Just the same way we're interested in what kind of research can you do for us, right? So anyway, this is about Gerardo's research. This is a student of Gerardo's, Dan Tennant. There's Gerardo. And Dan is actually receiving the Outstanding Thesis Award, right? And this was not only for the college, but this was for the entire university. And then actually his thesis went on to like the Western region. So what was his thesis on? It was on nonlinear electrodynamics. So basically Maxwell's equations, but using the assumption that Maxwell's equations at very high energies are not linear, but there's actually some nonlinearity. And this actually goes under the name of Born-Infeld electrodynamics. That's the type of deformation of Maxwell's equations that basically incorporates some nonlinearity. And it was published in Physics Letters B, which is a top-tier journal. Basically, they were making some predictions. So Born-Infeld electrodynamics is actually said to come out of string theory, or the low energy limit of string theory has Born-Infeld electrodynamics as one of its things. And basically, Dan and Gerardo predicted some effect where basically you have light passing through the field of a neutron star, that you would get some birefringence, the polarization would rotate. Is that more or less correct, Gerardo? Okay. So actually, and again, Dan won the Best Thesis Award and actually gave him money for that. This when this university had money. It was wonderful times. Anyway, oh, and Dan, he went on after this, went on to get a PhD from UT Austin. Then he got a postdoc in Canada at the Perimeter Institute, and then a postdoc at MIT. And I think now he's in the Bay Area somewhere. Gerardo, have you heard from him? Nothing recently? Okay. Anyway, he's in the Bay Area right now. Then the next research topic, so this is, Gerardo did some work with Ivana Pavic, who's here. She's actually now a tenured community college professor in Oklahoma. And basically they worked on classical general relativity and special relativity. So they basically looked at sort of orbits of particles in basically the special relativistic Coulomb problem. So the regular Coulomb problem you should solve with general relativity, but you can also ask the question, well, what if I look at the Coulomb problem just taking into account special relativity? And that was the outgrowth of this, and Ivana was the person who did the research. And this is actually a graphic from the paper that they published in the European Journal of Physics. So this is actually on the beach in Santa Barbara at a conference, so this is one of the conferences we went to. And actually this fellow right here is actually going to be the colloquium speaker next week. He's actually not a student. He's a famous Georgian physicist who was one of the originators of brain world models. His name is Mirav Gogberishvili, and he's going to be the speaker here next week. Okay, another one of Gerardo's students from 2017. This is the research project they worked on, basically charged black hole horizons and QED effects. So general relativity describes classical, sort of classical gravitational fields. So the big aim of theoretical physics is to try to quantize general relativity, to come up with a quantum theory of gravity. And this is something in that direction, okay? And so basically they looked at, how quantum effects could basically modify the horizons of black holes. And this is Jonathan. He actually went on to get it at one of the graduation dinners. I think that when Nancy was secretary here, so a while ago. Anyway, so Jonathan basically went from here, did his PhD at UC Merced, and then actually got a job in industry down in Santa Barbara. So very good. Okay, so this is some of my research. This is recent research. So recently I've been focusing on quantum mechanics and quantum gravity. So about a year ago now, I did some work with Tim Evans. He's currently on tenure track at Fresno City College teaching natural science. And then Michael Dunya, who's a PhD student at UT Dallas. And basically we worked on, actually we wrote a comment on someone else's paper. So it's kind of a jerk thing to do, right? We found something wrong with this other paper, right? And so we wrote a comment on it. And it wasn't one of those debates where it was like even close. It was like they did something really, really wrong. And so we pointed this out. So basically it was dealt with a model where you have a magnetic monopole, right? So these are hypothetical particles that exist in particle physics. And allowing for the fact that maybe the photon could be massive. So incorporating magnetic charge and photon mass, okay? More recently, I've been doing work in quantum gravity. So it's a type of phenomenological approach to quantum gravity where it's not like string theory, which is sort of a top-down, sort of high-level approach to quantum gravity. This is like sort of bottom-up. And what we do is we modify the commutators in quantum mechanics and look at what are called generalized uncertainty principle models. And so this is this work. This is with Michael Bishop, Joey Contreras, Jae-Young Lee. Joey is now a PhD student at UC Merced. This is his first year. Jae-Young Lee is actually in his second year at William & Mary. And basically, this is the work that we did. Actually, we again, were pointing out some sort of possible experimental handle for quantum gravity coming from gamma ray bursts. Then actually this is the next paper right here. So actually both actually this is from 2021, this is from 2022. So this is work again with Michael Bishop from the math department. So it's interdisciplinary. Joey Contreras again at UC Merced, and Pete Martin, right, sitting right here. So he actually was a co-author on this paper in Frontiers of Astronomy and Space Science, where we were again making a so this seems to be a theme. Like we just find other people's work and go like, nah, you're not right, you're not right. So, but you know that's actually a thing to do. Anyway, so it was a comment on the cosmological constant problem. So the cosmological constant problem is like a huge open issue in fundamental physics, and nobody has a clue as to how to approach it. There were ideas that generalized uncertainty principle models could, and basically our paper was to say no. So, all right, so this is kind of gross, and I'm inordinately proud of this last thing. So last year, Joey Contreras, Mike Bishop, and we won second place in the Gravity Research Foundation essay contest. So it's gross when people brag about stuff, so when you're a physicist and you write a paper and someone gives you money for your paper, that's, you know you've made it, right? Now, okay, it's only $700, but okay, what the heck. So anyway, this was, again, sort of an essay based on some of this work up here, and then before I got, so after we got the announcement that we won this thing, and actually in the past, people like Stephen Hawking have won it, he got first prize. Penrose won it, he got first prize. Frank Wilczek, he got first prize. And so that reminded me when my dad, so I was like really like, oh, I'm so excited about this. This is like fantastic. And I remember my dad said to me, like when I came to him in second grade, and I won second place in like a relay, you know when you run along and you hand up, so I won second place, so super proud. And I kept talking about it all day. And then he said, I'm tired of this. You know what second place is? It's the first loser. and then so when this happened, then I thought back to that. I'm like, okay, calm down. All right. So now I'm also, this is sort of an addendum. I'm also interested in doing a YouTube project, and this is something I'm working on with Mighty Lee. So there's an article called "What is Spin" by Ohanian. And if you ever have 2 hours to like be harangued at about like how spin actually is a physical thing, come by my office. I'll explain to you at length. So the thing is, this is a pedagogical article. Mighty Lee and I are working through some of the calculations, and eventually what I want to do is I want to make like a short 5 or 10 minute YouTube video explaining this, because everything on YouTube just follows Pauli's dictum. No, spin is a completely unphysical thing. Don't think of it as anything else. So Ohanian has a counter argument to that, and it's very cool. All right. So, and oh, so that's the end of. Oh, no, it's not the end of my talk. All right. So anyway, summary. Basically, publish. If you come work with us, what will happen? Publish research in top-tier journals. Attend national and international conferences. Basically, we have a good track record of getting students into PhD programs. And here's some of the PhD programs they've gotten into, or surprisingly, industry. Right? I mean, if you do research on black hole physics, like, why would industry want to hire you? But they do. Okay. And actually, community college and JC jobs. Like a lot of our students, when they get out, they get great tenure track jobs at local JCs, right? And again, here's our contact information, and basically here's like some of the recent papers that I mentioned, and actually here's the one with Peter, and there's his name right there. So Peter, shout out to you. That is the end of my talk. So, but one last thing. So this is just a general me as undergrad advisor telling you guys about conferences. Now this is a bit late, so if you haven't registered for this, you can still register today. You can still turn your abstract in today, right? But anyway, it's in Hawaii. Pete and I are going. Ooh, Pete, right? It's going to be fun, and I think Soban's going to go, and who else? Oh, Michael's going to go. So this is it's a 2-day, like, Far West Section American Physical Society meeting. There's money, both locally, and the APS will give you money to go there and give a talk. And this is the website, and again, probably, we should have done this last week, because then you would have had time to register, but okay. Anyway, this comes around every year, and so keep an eye out for it, and I'll try to tell you guys about things like this. Anyway, thanks a lot, and that's the end of my talk. And so in light of the time, does anyone have a question? Yeah?
I keep asking this. What are the prerequisites to take this your research?
Oh, that's another. So most of the research publications were actually with graduate students. I think Gerardo and I, we published 1 or 2 articles with undergrads, like Mike Ragsdale. So there are some projects, like the YouTube project, right? There's a possibility for publishing something out of that, but I mean, my main aim is I want to get YouTube famous now. I'm tired with, like, I publish stuff in, like, academic journals, and like maybe 100 people read it, maybe, right? But YouTube famous, no. So, but more seriously, probably after you take Dr. Ho's 102 course, the modern physics, that would be a good time to come talk to either Gerardo, myself, or Tori, Dr. Vitale, to look at doing theory research, right? So yeah, so I'd say after 102 would be a good time. Now we do have some projects for undergraduates, and there are pedagogical journals that we could publish stuff in. So, and that's always my aim, is to basically get a student a publication, because that's really what will help you, like, going forward. Oh, and let me say, so Tori is also part of the theory group, even though I didn't include him on the slide, sorry. But he's going to give, so the reason he's not giving a talk is I asked him to give a talk, and he's like, I've got too many students. So first of all, Dan, you no, I'm joking, obviously. So, and then the second thing, he is actually going to give a longer talk December 2nd. So Dr. Grassi is going to give a talk September 30th, and then Tori is going to give a longer talk. Are you going to give a talk?
I think theoretically I got invited to give a talk in chemistry October 22nd. But after that, they didn't even ask me for abstract. And also I owe abstract for Sacramento State. And that's in November or something.
Oh, so actually, we'll send all that stuff to me, and if it's on campus, I'll advertise that, and actually I'll keep October 2nd clear, so that basically
22nd.
October 22nd, yeah. So I will send everyone over there. So that'll be easy for me. Then I'll get a free colloquium out of it, and I don't have to organize. And then we'll send people to give you to your talk.
Okay, I need to go confirm. I haven't got time to write an abstract.
Did you say October 22nd?
So Tori's going to give a talk December 2nd, so definitely come to that. And Don, with that, come on up. Sorry for taking your time.
Guys, we're gonna make it quick. Good thing. I want everybody to turn around and look at our poster up in the corner. That's our poster. I don't need a PowerPoint. You see that big one that says Physics Outreach? You guys can definitely read that, dude, right?
Next to it is mine.
There you go, exactly. You can read her too, but you gotta go up there to see it, right? So anyway, hey Tristan, yeah, you guys all come down too, man. Tristan, and you guys get the ice cream out of the back, there's that door locked. The good news is you guys are gonna get ice cream. Okay, that's the good news, we're gonna make some ice cream. Now, what I do, guys, here is I run the Physics Outreach Program, all right? And so I do a few things. I have a blast every day, one thing. Every day I come to school, I'm always having fun. And these guys are actually a couple of my students that took the class before. And no matter what you do in life, this class will help you. Getting up in front of people and talking. Because when you do research projects, you're gonna have to get up and present those to people, right? Or you get up and you have to defend your thesis, right? You're gonna have to get up in front of people and talk in front of people. So this class will help you guys tenfold in that. Not only that, but you guys that think you know physics, and then all of a sudden you try to start explaining to people and they're going like this, yeah, you'll realize the old adage, until you've taught physics, you really don't know physics, all right? And so you'll learn that aspect of it too. The good thing is also, we go from the littlest kids to the biggest kids. We go from little PK, like we were doing, you guys know what TK is? That's toddlers. That's like 3 years old. And do you think they can learn physics?
Oh, yes.
Hell yes they can, no problem. I'll be honest with you guys, I wish my college students could absorb as fast as kindergartners. I mean, kindergartners just suck it in. And that's our problem. See, that's my big aim is, you guys are the few people that filter through in America and so forth, and filter through and learn math and science, right? I mean, all the other countries, they teach kids math and science, not in America. Okay? And so what we have is we have all these educators out there thinking, and they got all these different theories how they teach, you know what I mean? And we got all these educators, and all we do is, we get these kids coming through here, and they don't know math and science. And it's a really hard thing. We beat our heads against the wall, hoping that in America we need to learn math and science. Now what we got going over everybody else in the world is we got diversity and Yankee ingenuity, and that are huge. But if we ever train our students to know math and science, look out. We will smoke everybody in the world. It won't even be close. So that's my main aim, is to get that word out there, train teachers, and remember, this is college teacher, everybody, right? How to teach math and science, because guess what? You can teach any subject the way we teach physics. See, that's the beauty of, you guys all know, because you've been teaching physics many years, is they have all these different theories about teaching. We've been teaching physics the same way forever. You know why? Because it works. It works, and you build it up, it builds up, you know, and it all works out, and you look at it, and it's beautiful. And that's the way it should be, okay? So enough of that ranting. Let's go ahead and make some ice cream.
Half a?
Yeah, just do about a half a liter. But that's pretty big credit. You like 3/4 of a liter of each.
You need more milk, I have a...
We don't use milk, see. That's what they use over in the, yeah, we do make a lot better ice cream. We use half and half and whipping cream, you know what I mean?
Wow.
And brown sugar. So nothing but fat sugar in our ice cream. And the beauty is, you guys have heard of Fresno State ice cream, right? They make really good. And I know Danny over there in the creamery. He makes great ice cream. This is better. This is like, everybody that tastes this, I can brag about it every single time. I can always brag about it. Now, I do have to be careful. My students sometimes will put too much brown sugar in it. And then you guys will all be flying home, you know what I mean? But sometimes when we go to schools, we're going to leave anyway. What the heck, right? Light up the kids. Put plenty of sugar in it. All right, you guys got it? Who's got glasses on? You all got glasses on? Good deal. Good deal. And so if you guys have seen the trailer out front I have out there, that trailer, that big trailer says physics on it, right? And that van out there, that's what I have. That's my rig. And the class I teach is a 2-hour lecture on Thursday night, and that's where you learn to do the physics and learn how to teach. And then you have a choice of either Wednesday or Friday, and that's the lab. What are you doing, Ben? You need to get up here and help too, man. I just saw you. He's Ben's new student too. And then that's when we go out and do the teaching. And that's when we go out. And we not only go to schools, we go to all kinds of things, like girls STEM programs, right? We go all over the place. We go to Steve and Kathleen's planetarium over there with kids. So we making it now? Right on, good deal. So you guys can speed it up, because we got to get everything out. And then, what's that? Liquid nitrogen, exactly, exactly. And of course, we have to teach the kids, they see something like that, they think it's hot, steam. You know, and they don't realize this type of weather, we report it everywhere, right? I mean, you guys know what I mean. But I really truly believe, guys, that as I've been to just millions of schools, kids love to learn in all ages. They love to learn. And it's our problem is that we're not teaching them well. These teachers, they'll tell you they don't know how to teach science and math. I mean, I'll go into a school and I'll see a third grader answering the science questions right, and I can tell the teacher over there mouthing the wrong answer in the back. Doesn't know the answer, you know what I mean? And that's not a good thing, right? That's not a good thing at all. So this is our main process, is we're trying to train teachers. Now, I'm fighting the education department all the time, because they've got their own, like I say, all these fancy theories, how they want to teach and all this stuff, and I'm still fighting. And I got a lot of people behind me. I mean, our whole department is really behind this program, what we do. And then we also do other stuff, and we're going to bug you again, Tori and Mihai. We go out to high schools and recruit, like I was talking about. That's an important thing, like what you're doing. That is a good thing, it really is get these high school kids here. And I've got one for you, Tori. This kid came in, he's from Clovis North, all right? And he comes in, and he wanted to do outreach. He emailed, and I said, come on by, right? The next thing I know, he's talking, and I go, well, you know, how much math have you had? And this kid, as a junior, guys, had differential equations in linear algebra, okay? As a junior high school. Now, all right, now that doesn't top it off, right? All right, now, you know what he did last summer? He did a project at Carnegie Mellon. You know what I mean? So you got to come one night and help recruit this guy. Because he wants to go, his bag is he wants to go to computer science. But you can imagine, he could probably get offers from just about everywhere. But I'm trying to convince him. You know, a small school like this, guys, you're going to get an incredible amount of, you guys ready? You dishing it up? You're going to get all kinds of help from everybody here in this small school, and you will get no better undergraduate education right here, I'm telling you. Every time we send students out, they're well prepared. And you do, you've got a lot of stuff to choose from. And and Doug's finding out now too, and everything, the cosmology, everything's just coming together now. It's just all stuff now. And the neutrino physics, that's huge now. That really is huge. Let alone the space telescope. We're afraid of the space telescope. Isn't that incredible? Are you guys seeing the images we're seeing out of that thing? It's unbelievable. That's why we've got the best stuff in the world. We just got to show it, huh? We just got to show it. All right, we're going to dish up ice cream. You guys can kind of get it as you want to come. And then, Doug, you can make it a wrap up and call it a day. And we're good to go.
Yeah, well, let's thank all the speakers once again. Come on down and get ice cream if you want. There's still plenty of cookies.
There you go, get some cookies too, guys. Definitely. You guys giving them a big amount, we got that one. And some of that ice cream. That'll be good for your blood.